So in this episode, we're going to deal with the set theory and combinatorics. In particular, we're going to calculate how many subsets are there inside a set. So let's go.
Okay, so today we're gonna talk about the problem of number of subsets inside a set of n elements. So we have the theorem here. Let A be the set with n elements. Prove that the number of subsets of A is 2 to the power of n. This is n, okay? So let's give it some try. Okay, so for example, we have a set A1 of 0 element. So we know that the subset of A1 is just a subset of A1. It's just A1. It's just A1 itself, right? A1 itself. So that actually 2 to the power of 0 element, that's just one subset, right? So if A2 is the set of 2 elements, like 1 and 2, so we have the subset of A2 are gonna be which set? So it could be it could be, well, the subset could be 1, right? The subset could be 2, and the subset could be A2 itself, which is 1 and 2, and also the subset we still gonna also have the null set as the subset as well. So that was a total of 4 subsets. So that was 2 to the power of 2, right? So we have 4 subsets inside the set A2. So that's 2 to the power of 2. And let's try with 3 elements. Okay, so for example, for the 3 elements set A3, we're gonna have 0, 1 and 2. So the subset of 0 of A3 gonna be okay, so the empty set and 0 and 1 and 2. Okay, so and then that's 0 element and then 1 element subset. So for 2 element subset with 1 and 2, we also have 1 and 3, and we also have 2 and 3. So and last but not least, we also have 3 element subset, which is 0, 1 and 2, which is the subset A3 itself, right? So and 2. So this is actually 1 and 2. I made some mistake here. This is 0 and 1. This is 1 and 0 and 2. 0 and 2. And here we have 1 and 2. Sorry. So here we have 8 subsets. So 1, 2, 3, 4, 5, 6, 7, and 8 subsets. So that's actually 2 to the power of 3. So in general, for the set AN with n element, so with n element, so that means the number of elements in AN is equal to n. Then the subset, then the number of subset of AN. So number of subset of AN gonna be generally 2 to the power of n, as the theorem has stated. As the theorem has stated. So let's try to prove that. So for a subset with k element, k is between 0 and n, including 0 and n itself inside A, which has n element, I mean the set A has n element, there was c, k, and ways to form that set. So therefore, the total number of subset of A is the sum of k equal to 0 to n of ckn, which is because k is running from 0 to n. So by that we can apply Newton's binomial theorems. So which state that x plus y to power n is the sum of ckn x to the power of n minus k, y to the power of k, and we're going to take k from 0 to n. Or the vice versa, we can take x to the power of k and y to the power of n minus k. Still ckn, we take the sum from k to n. So we're going to apply Newton's binomial theorems to the expression the sum of ckn, k from 0 to n here. So the sum of ckn, k from 0 to n is just the sum of ckn multiplied by 1 to the power of n minus k times 1 to the power of 1 to the power of k with the sum from k0 to k with the sum taking from k equal to 0 to n. So this expression by applying Newton binomial theorem is actually 1 plus 1 to the power of n, which is 2 to the power of n. So and we have known that the total number of subset of A is this sum itself, the sum from k equal to 0 to n of ckn. So so therefore we have proved the theorems. So for a subset, for a set A of nth element, we have 2 to the power of n subset, and as a matter of fact, the theorem is proved.
So in this slide, I will give a piece of code that implements those theorems we have just discussed. As you can see, whether you calculate the number of subsets by the formula, which is n to the 2 to the power of n, as we do in Pole 26 here, or you just calculate by summing the number of combinatorics possible, the result is going to be the same. So in this case, we are counting number of subsets in the set of 6 elements, which in both calculations gonna generate 64.